Hello everyone. When we see different mechanical systems and components in actual application, we can see that system and components are subjected to different forces and different movements working on it. So today we are going to discuss a very important phenomenon for the systems and components which are subjected to different forces and movements when implemented somewhere, and that is vibration. Today we are going to discuss some basic terminology related to vibrations. So, what is meaning of vibration, or when it is said to be a body is vibrating? A body is said to be vibrating if it has to and fro motion. When any body is subjected to and fro motion, it is called as body is vibrating, and this body continues to vibrate indefinitely in absence of friction or resistance to that vibration. So basically, when there will be no friction or also resistance, it will be vibrate for indefinite amount of time. Now vibrations are actually nothing but it is conserving energy from one form to another form. So when any body is displaced from its equilibrium position, that is work is done on the force which is displacing that component from its mean or equilibrium position, and energy is stored in form of potential energy or in form of strain energy. So energy is stored in form of strain energy. That strain energy is released, that will be converted into kinetic energy, and it reaches to the maximum kinetic energy at the position of equilibrium, and again equilibrium is get displaced in another direction, and it reaches to the maximum strain energy, and kinetic energy is conserved into strain energy, and this process continues till it is getting damped or till it is resisted by some external force. And if any external force is not there or any resistance is not there, it will continues to oscillate, or it is continues to vibrate for indefinite time. Then there are few concepts are there as far as study of vibration is concerned. So first is what is free, or also called as natural vibration. So free vibrations are nothing but vibrations in which there are no friction and external forces are uh, applied after once initial release of body is excited. That is called as what the free vibration. So in free vibration there will be no any resistance equal to 0, and no force which will resist the motion of body. That is called as free vibrations. Then second phenomenon or second definition is forced vibration. So forced vibration are called like when a repeated force continuously acts on a system, the vibrations generated into that body are said to be forced vibration. So here there will be a repeated external force is there. Repeated external force is present in case of forced vibration. The next term is damped vibration. So when energy of vibration is gradually dissipated by friction and other resistances, the vibrations are called as damped vibration. So here now energy of vibration is dissipated. Energy is dissipated. And as energy is getting dissipated due to the resistance or due to the friction, the vibrations are not continuous for indefinite amount of time. Then there are few terms are there related to vibrating system. First is something called as period. The period is nothing but it is time taken by motion to repeat itself, and it is measured in terms of seconds. Whereas cycle is motion completed during one time period. Then frequency is number of cycles of motion completed in 1 second. How many number of cycles completed in 1 second is called as frequency. Then there is one term which is resonance. Now when we talked about this time period is denoted as T. Frequency is denoted generally as F, but here we will denote the frequency, angular frequency, so it is denoted with omega, or also it is denoted with F. But when it is frequency, when we talked about frequency, there are two different frequencies can be possible for a body which is vibrating. One is natural frequency of system itself, whereas second one may be frequency of external force applied on the body due to which the vibrations are generated. So there are two different frequencies are there. One is its own frequency, and second one is the frequency of force which is acting on the body. And when this frequency of force acting on a body matches with the natural frequency of this system, the state of resonance is occurred. And when the state of resonance occurred, at that time the amplitude of vibrations becomes too violent, and that may be results into damage of the system. So here what happens is natural frequency will matches to the frequency of system, or frequency of external force. In that case it will be resulted into resonance. Then different types of vibrations. There are basically three different types of vibrations are there. Longitudinal vibration, for example, assume that likewise one shaft is there. At the end of that shaft one heavy disc is connected, and this disc is subjected or excited in this direction. This type of vibrations are called as longitudinal vibration. Whereas if we consider a shaft at the end of which disc is connected, and if it vibrates in this direction, it is called as transverse vibration. And third one is torsional vibration. So when there is torque acting on this, so it will be acting by torque, or we can call it as movement. And in that case, this torque is represented as the motion in longitudinal and transverse vibration is denoted with x. Here in case of torsional vibration, the motion is denoted with theta. Then basic elements of a vibrating system. So basically there are three elements of any vibrating system as such. When we convert the any system into a mathematical model, we need to convert all the elements available into that system in either of these three elements. First will be the inertial element. Inertial element is represented by lumped mass or lumped movement in case of linear or torsional vibration. Whereas second element is rotating element, restoring element, and restoring element is massless linear or torsional spring. Whereas third is damping element. Damping element is nothing but massless damper of rigid elements. For example, if we consider a system spring mass damper system. So inertial element is represented with M as lumped mass, whereas restoring element, the characteristic of restoring element is the stiffness. So this will be represented by spring with stiffness K, and damping element will be nothing but it is a damper with certain amount of or definite amount of coefficient of damping, and that is represented as C. Then next term comes into picture. As far as vibration is concerned, it is degrees of freedom. So what is degree of freedom? These are nothing but number of independent coordinates required to describe a vibratory system in complete manner. That is what the degrees of freedoms are concerned. And the degrees of freedom may be single degree of freedom, 2 degrees of freedom, or it may be several degrees of freedom, or it may be multi degrees of freedom. For example, if we consider an example of spring mass element, and this entire system can be represented with the motion in x direction only. So this is what called as single degree of freedom. Similarly, if we take an example of pendulum which is displaced from its mean position, and the theta is only required to describe the entire vibrating system in nature, so it is called as a single degree of freedom. Whereas if we consider spring mass system, but there are two masses connected in series with the help of two springs. So if it is m1, if it is m2, k1, k2. Now here the two coordinates are required, x1 and x2, in order to describe the motion of this system, and this is called as what? 2 degrees of freedom, or vibrating system with 2 degrees of freedom. Similarly, we can take example of pendulum also. In that case, there will be system something like this. For this, we need to have theta 1, we need two coordinates to describe this entire system, which is called as 2 degrees of freedom. Similarly, in the similar fashion, there may be possibility of several degrees of freedom. Like, assume that there are 4 discs are mounted on shaft which is subjected to certain amount of rotation. For example, if this is represented like this, which is supported, the shaft is supported at its end with bearings, and this will have certain amount of T1, T2, T3 and T4. So this is called as what? Several degrees of freedom. Whereas if I consider a fixed beam with some uniformly distributed load on it, so this system is called as multi degrees of freedom vibrating system, or rightly it is called as indefinite degrees of freedom system. The next is simple harmonic motion. Is what? In case of simple harmonic motion, the to and fro motion with its acceleration always directed toward the mean position, and that acceleration is proportional to its distance from the mean position. And in SHM, the displacement is represented with the help of x equal to a sine omega t. So we can able to take the first derivative, that is x dot, or it is nothing but dx by dt, can be written as a omega a cos omega t. Similarly, if I take second derivative of displacement, or it is acceleration, it can be written as minus a into omega square sine omega t. But we know that a sine omega t is nothing but x. So what we can write is x double dot will be equal to minus x into omega square. So this is what the characteristics of simple harmonic motion. Nature, all the vibrating systems are considered, or usually considered, motion is considered as simple harmonic. Now next is, now we will see how to write equation of motion for vibrating system. Now there are many different methods are there to write this equation of motion. Here we are going to consider energy method only. So in energy method is what? It is conservation of energy. The total amount of energy in conservative system remain constant. So we can write kinetic energy plus potential energy will be equal to constant. So if I take derivative with respect to time of kinetic energy plus potential energy will be equal to 0. Now, if I consider a spring mass system with mass m and spring with stiffness k, now in that case, the kinetic energy can be written as half of m into v square, so it will be written as x dot square, whereas potential energy can be written as force into displacement, and force is what? It varies from 0 to kx. It varies from 0 to k into x, and so as it is varies from 0 to kx, it will be average forces kx by 2 into x, or it can be written as kx square by 2. Now if I write in this equation of d by dt ke plus p is equal to 0, I will get d by dt half of m x square plus half of x dot square plus kx square by 2 will be equal to 0. Now if I solve this equation, it will be half of m as constant, x dot square, so it will be 2x dot, and derivative of x dot is x double dot, plus k by 2 is constant and x square, so that is 2x dot, 2x, it is 2x into x dot, so it is 2x dot into x is equal to 0. Now here this 2 get cancelled, this 2 get cancelled. If we divide entire equation with x dot, it will also cancel out. So final equation we will get is mx double dot plus k into x is equal to 0. But what we know for SHM, x double dot will be equal to minus x into omega square. So if I replace x double dot with minus x into omega square, so it will be m minus m into x into omega square plus kx equal to 0. So this x get cancelled. So finally, if I find out omega square, that will be equal to k by m, or what we can write is omega is equal to under root of k by m, and this omega is nothing but natural frequency of that vibratory system. Now then next we will go for damping. Now what is exactly damping is? Damping is an external resistance offered to motion of vibratory system. Now this external resistance may be due to friction, or may be intentionally some additional resisting force may be implemented into system, so that it get vibrations may get damped out, and it is very important to damp out the vibration, or otherwise the system continues to vibrate in nature. So now if here if I represent this, if I take this damping also into consideration, the system which we have shown in the previous one as spring mass system with mass m, stiffness of spring k, and now here damper is added in form of dashpot with the coefficient of damping as c. C is coefficient of damping, and this c is represented in terms of Newton second per meter. It is actually force per unit velocity. Now here in this case, if I write equation of dynamic equilibrium for this system, that will be written as mx double dot plus cx dot plus kx is equal to 0. So what the equation we have seen previously, that equation will be modified like this. There will be a component cx dot comes into picture, and that is due to damping coefficient, and damping coefficient is nothing but it is force applied per unit velocity. Now this can be rearranged as x double dot plus c by m x dot plus K by M x is equal to 0. Now this is a form of second order differential equation, and solution for this equation can be written as x equal to a e raised to alpha 1 t plus b into e raised to alpha 2 t, where a and b are constant and alpha 1 and alpha 2 can be determined as c minus c by 2m plus minus. So for alpha 1 it will be plus, for alpha 2 it will be minus under root of c by 2m square minus k by m. Now here one term comes into picture, that is called as what? Dampness or degree of dampness, or also called as damping factor. Here if we see ratio of c by 2m square to k by m, this ratio is called as damping factor. Now here one term come into picture, damping factor, which is represented as zeta. Now what is the zeta is? Zeta is c by 2m square ratio of c by 2m square divided by k by m and whole under root of. So this is what represented as zeta. Now this can be further simplified as, if we simplify it, it will be c by 2 into under root of k by m. So this will be the equation for in most of the cases. So we can write c, that is damping coefficient, will be equal to 2 into zeta under root of 2k. Now the value of zeta will be very important as far as any vibrating system is concerned. So based on the damping factor, the vibrating system may be under damped. In case of under damping, the damping factor is less than 1. In case of over damping, the damping factor is greater than 1, whereas in critical damping, the damping factor will be equal to 1. There may be one more category where the damping factor is equal to 0. This is nothing but, this is free vibration. There will not be any resistance to vibration, and the system will continues to vibrate. Now if I represent the vibrating performance of vibrating system on displacement versus time plot, like this. Here on y-axis I will take displacement x. Now I will plot one by one. First I will represent the system which is having zeta is equal to 0. When zeta is equal to 0, the system is something like this. The system vibrates in this nature. So there will be no any change in the amplitude for number of cycles. So the system continues to vibrate, and for this the value is zeta is equal to 0. So this is free undamped vibration. If I take another example, second one, as critically damped system. So in case of critically damped system, the system may be represented something like this. There will not be any oscillation as such. The system is, the displacement reaches somewhere at 0 and it continues. So there would not be any type of oscillation which will occur into nature. Whereas for this, the value of zeta is 1. So this is critically damped system. Now if I take overdamped system, if I take an example of overdamped system will continues with displacement, and displacement will become zero after very large amount of time. So it will take time to get it damped out. This is called as overdamping. Now there will be one more type of oscillations are possible, and that are called as what? Critically damped system. Sorry, not critically, under damped system. And in nature, most of the cases the systems are under damped systems only. So under damped system performance will be something like this. So in this case of under damped system, if I find out what is amplitude of xn and xn plus 1, there will be a constant decay is observed, and this is called as what? Critically damped. That is what zeta is less than 1. Now there are few characteristics are there, like for underdamped system, when zeta is less than 1, in that case we can write omega d will be equal to under root of 1 minus zeta square, into omega n. Now here you can see there will be there will be natural frequency of system, there will be frequency of damped system, or damped due to the frequency due to damping. And when there is zeta, when we talked about zeta is less than 1, you can see this product becomes to be less than 1. So that always in case of underdamped system, omega d will be always less than omega n for underdamped system. And in case of critically damped system, you can see zeta is 1. So you can able to get that this WD will be equal to WN, and for overdamped system, WD, that is frequency of damping, will be greater than that of natural frequency of system, and which is actually not possible, and it is not desirable also. Now in case of underdamped system, when zeta is less than 1, the continuous decay in the displacement is observed. And if I represent that continuous decay like this, the system vibrates something like this. So if I take this as x1, amplitude in second cycle x2, and continues. So what we can write for underdamped system, in case of logarithmic decrement, we can able to write here xn to xn plus 1 will be equal to x0 by x1 equal to x1 by x2 equal to x2 by x3, and so it will be continuous. And also it can be written equal to e raised to zeta into omega n into time period t. Also this can be written as xn plus 1 can be written equal to 1 upon n into x 0 by x n. also. So now from this, if we see this decrement is actually following the logarithmic way. So if I write for logarithmic decrement, or if I are interested to find out logarithmic decrement, which is represented with delta, can be determined with the help of natural logarithm of xn divided by xn plus 1, or this can be also written in terms of zeta into omega n into time period. So with the help of these two, we can able to find out what is logarithmic decrement. Now we will come to the two cases when the cantilever beam is subjected to free vibration and simply supported beam subjected to free vibration. For example, in case of cantilever beam, if I consider a beam, now here the mass of beam we are neglecting, so the entire mass is only applied at the end of beam, and that is called as equivalent mass. Now for this typical, the stiffness of this beam can be determined with the help of K is equal to 3EI divided by L cube, where the L is length of beam and E is Young's modulus, I is moment of inertia of beam, and that will varies with respect to its own cross section. So here if I write equation mx double dot plus kx is equal to 0, so k can be replaced now with this and may be written as mx double dot plus k is 3ei divided by L cube into x is equal to 0. Now omega can be determined, or omega n, not omega n can be determined. For this case it is k by m, so it is 3ei divided by L cube into m. Here m is equivalent weight, not only the weight of end mass, but if the beam is not massless, then we have to consider that equivalent weight of beam also. Second one is simply supported beam. In case of simply supported beam, for example, they may be supported at both ends. Here we are considering the mass is only acting at the exactly midpoint, that is L by 2, and this length is L. Now in this case, stiffness of this spring can be determined with the help of 48 EI divided by L cube. So here in this case, omega n can be determined with the help of under root of 48 EI divided by L cube into m. So this is all about the basic terminologies of vibration, and this is very relevant with respect to experiment we are going to conduct with the help of virtual lab. So just you can go through all this mathematical forms and all the fundamental concepts of this vibratory system, and we will conduct the experiment on determining different parameters of cantilever beam and simply supported beam with the help of virtual lab.